Welcome, everybody. The URL there is where on my site I usually keep the PDFs of my slides. I will also upload them to the PyCon side. What's right there right now is not exactly what I'm going to present. I promise this afternoon I will update everything. As a kind of a bet, I picked the least fascinating, the least exciting and most indispensable chapter of the third edition of Python in a nutshell, which is already available in an early release. That's chapter 5, which is about errors and exception handling. Incidentally, if it still works, O'Reilly may have mixed something with the I'm sorry, but the Python 45 code should allow a discount at checkout if you get the ebook, and what you get is, as usual with O'Reilly, DRM-free ebook in all forms and permission to copy them on all of your devices. And the reason I have the slide is not so much because I like to sell more copies, because at these discounts it doesn't really matter. It's because I want to get feedback while we can still do major changes, we being me and my two co-authors, my wife Anna and Steve Holden, the initiator of PyCon many, many years ago. All right, exceptions in Python are not always errors. This is crucial for people coming from other languages where avoiding exceptions is important because they always mean errors. They can be errors, like this 1 divided by 0 exception. They can be perfectly normal things, such as an iteration is finished. Remember, I will use EXC all the time and pronounce it exception for shortness to fit on the slides. The core thing that every Python programmer needs to know to deal with exception is a try statement. It's fortunately, in 2.7 and 3 anything, become completely regular. You can have an except, more than one except. You can have an else, only if you have except. You can have finally, optionally at the end. You can also have just try finally, in which case you're not handling any exception, just doing cleanup work at the end. A few things that are absolutely important. When you have except clauses, put the narrowest one first, because the matching is strictly beginning to end. So if you match a more general exception, the further except clauses that might match more closely will not even be looked at. So be careful with that. Else is a somewhat unpopular clause, but I find it precious. It means execute without any exception guard what follows if no exception have been caught so far. You can often get the same effect by moving whatever is after the else after the whole try except statement, but it's much more explicit, much more readable to have things in the else clause. Another not well-known thing is that in the finally clause, you cannot have continue. If you have a continue, Python will scold you and give you a syntax error. But if you put there a break or return, Python will not tell you anything, but your exceptions will be hidden, swallowed, disappear. And that's so unexpected that it is sufficient to make your code completely unreadable. Also, if you think about the semantics of try finally, there's never any reason to say and finally return or finally break. So just use a linter or your own discipline to never use break or return. Sometimes you want to be the one initiating the exception by raising the exception object. In Python version 2, which I always call V2, while Python version 3 I always call V3 for shortness, the whole book is about both Python 2.7 and Python 3.5, so the differences and distinctions and so on are mentioned over and over. It could be a subclass of exception, in which case it would be instantiated for you. That was never a great idea, and it doesn't work in v3 anyway, so just avoid it. Keep your code clean, always raise an object. Or raise without anything. That must be in an except clause, directly or indirectly. Could be in a function you're calling from an except clause. It just re-raises the exception you just got. This is a very common thing. You want to do some cleanup, some arrangement, and then just let the exception propagate. When do you want to raise? Well, if you're playing old-fashioned poker and you have that hand, you probably want to raise, but that's a different meaning of the word raise. When you want to give some diagnostics where Python wouldn't. For example, suppose you're writing a cross-product function, which for some reasons that have to do with the semantics of the library you're writing, cannot accept empty sequences. If either sequence is empty, that's a value error. Type is correct, but value is not. Otherwise, it does the normal way. Of course, you could use ITER tools to do it, or whatever. But the point is, I am not checking all the other things that could be wrong with sec1 and sec2. For example, if they're not iterable, Python itself will check for you when you try to iterate on them in the list comprehension and raise a type error. Never duplicate error checks that Python intrinsically does for you anyway. That just clutters your code to no good extent. If you want to raise a different error in those cases, use a try except around the relevant code for that purpose. In v3 only, it's one of the big improvements that I see in the language, there's an automatic wrapping of exceptions. Instead of having the traceback and the exception as two separate things that just happen to be there at the same time, the traceback is held by the exception object. You can change you can get a copy of an exception with a different traceback object with the with traceback method. That's not all that frequent a need, but if you ever have it, that's how you do it. But the most important thing is that automatically the last exception that was caught and is being handled becomes the dunder context attribute of the new one. So that happens automatically for you. Explicitly, you can also set some exception object as the cause of the new one, with the new form of the statement raise the new exception object from none means no cause, or from existing exception object that sets the dunder cause. What's the effect? It's diagnostics. So this is a function that wants to compute the inverse, and we decide that inverse of 0 is not really a zero division error, it's a value error, because we could be computing the inverse in other ways than by dividing, whatever. It needs to be a value error. However, to avoid hiding what really happened, what's the cause of that value error, we use the raise from form. And in this case, if it just propagates up to the top level, the diagnostics says that the zero division error was the direct cause of the exception that actually happened. Note the exception that actually propagates is value error. So if you want to catch it, it's try except value error. But if the diagnostics happen, the dunder cause being set by the raise from statement, you get a much more precise diagnostics. Similarly for context, context is typically not something you set explicitly, it just happens. Suppose that in the handler, in an except clause, you just happen to have a bug. So this is pretty explicit, right? The try 1/0 obviously raises a zero division error. You catch it in the except, where accidentally you're trying to sum a number to a string, which is an error of its own. So in this case, instead of just seeing the type error, as you would have in V2, in V3, if this propagates to the top level, what you see is a zero division error, and during handling of the above exception, the following exception occurred. So again, what's propagating is the inner one, but it carries along the context in which it was raised in the under context, which is sometimes very useful in pointing out exactly what's happening, where your bugs are. Another alternative, an alternative to try finally, but sometimes also to try except, is the with statement, where you need a context manager X, which means it has a dunder enter method in which it may return something that you catch with the as something, as Y in this case. And then imagine that the block that's literally inside the with is in fact executed inside the try clause of a try except finally. The point being that if there is any exception, that exception, here I'm using the x-info function of module sys to get the triple for the exception, is passed through the dunder exit method of the context manager, which may decide whether it propagates further or not. Not the way I've spelled it. If not, x dunder exit and so on, raise. If x dunder exit chooses to return true, that means the exception has been handled, it must not propagate further. That's why it's kind of like a try except block. And finally, if no exception has occurred, the dunder exit is called with nonce, meaning, okay, we're exiting. Why is the distinction important? Because this is essentially the same as the resource acquisition is initialization idiom of C++, but in C++, you do get to run the destructure, but it's not immediately obvious whether it's a normal exit or an exception. With a Python with, you do know immediately. So for example, in a context manager like SQLite 3's connection, the exit in case of exception has a rollback of whatever you've been doing in the block, so you don't have half of the operations destroy your database. In case of success, it has a commit, so that the database reflects the operations you've done. The best way to make a context manager, the simplest in most cases, instead of writing a class with dunder init, enter, and exit methods, special methods, is the context-lib context manager decorator of the context-lib standard library module. Essentially, you use typically a try except finally to map exactly what the context manager will do, except you yield the result that you'd normally you can use in the as something part of the with statement. Moving on, we finally have, into 7 and better, a sensible way to handle exceptions in generators, and therefore to have the caller, which in a sense, in many cases in modern versions of Python, is more a controller of the generator object that's executing, throw an exception inside the generator. That's generator throw. Possibly the most common case is the close method, which is just exactly equivalent to throwing an instance of generator exit. Note again, this is another case, though more modern, newer one, where an exception doesn't mean an error. It's pretty normal for the controller to decide to terminate the generator objects it's using. Most generators should just do the when they're getting the new, yielding a previous result and getting the new stuff, so result equal yield previous, should do that in the try clause of a try except, so at generator exit they can do cleanup. Of course, they can also refuse to exit, but that's not normally the intent. It's just to afford an opportunity to do cleanup exactly where it's clearest and simplest. I'm pretty sure you're all familiar with the exception propagation concept around the stack of calls. Just one thing I want to point out is that all the exception handling, all the finally close, and possibly at the very end sys.excepthook, whatever function you may have set, or the default one, all take place before any termination function you register with the atexit module. It's better not to rely on this, not to have things depend too heavily on order in which they're destroyed, but if you have to, this is the order Python gives you. The atexit-registered functions are last. Now, exceptions are one of the few places where Python really, truly, desperately cares about inheritance hierarchies. Why? Because the way the except clauses work is to catch any instance of the type, the exception types you list in it, which means also any instance of their subtypes. Therefore, the hierarchy of exceptions, standard exceptions, is very important. In version 2, we tried to make sure that all errors came from standard error with many types and subtypes, and exceptions that aren't really errors were still inheriting from a base exception indirectly, but directly or indirectly, but not from standard error. That didn't really work out too well. On the other hand, the environment error blocking together all the I/O and OS errors. So to be perfectly honest, whether some anomalous situation during I/O is done for us by the operating system, so whether something is an I/O error or operating system error isn't usually immediately clear. Like what? However, in version 3, things have been simplified. We don't have the standard error level anymore. So essentially, both non-errors like stop iteration and actual errors inherit from exception. Only the to exit kind, generator and system exit, and the keyboard interrupts inherit from base exception and not exception. Perhaps more interestingly, the environment error and I/O error are now just synonyms for the OS error, because in the end, that's the real semantics. This is an error the operating system has reported to me during some system call. On the other hand, there's a bunch of new classes which subclass directly OS error, which are pretty obvious and specific. One example is file not found error. That's an error we've all met and we all know what it means. Whoops, there should be a file here and there isn't. So for example, in version 2, first version of this, almost inevitably, when you quote an I/O error, you had to start looking at its kernel to be, okay, what happened? Is it a missing file, a permission problem? Also the fact that missing file is encoded as inoent is not immediately obvious to anybody but C programmers with Unix background, I suspect. So this was a typical treat. We're just trying to read and return the contents of the final path, otherwise returning the default. In version 3, I believe things become much more readable, essentially because all we do is catch the very specific file not found error and return the default. Anything else, any other I/O error, or OS error, or environment error, call them as you wish, will just propagate, like we had to do explicitly with that raise over there. So with all these standard exceptions, do you ever need to define your own? The answer is, if you're writing a library or framework, you probably do. So why? Because the client code that's client of your module or package can easily catch all the exceptions that are specific and peculiar to your packages and to your package and handle them some way. Best practice is to define a class commonly called just error within your module, so your module.error or your package.error, which directly subclasses exception and only provides a docstring. And then if you need to get more specific, you further subclass that. For this latter purpose, I have this idiosyncratic taste. I believe this is the one place in Python where you really want to use multiple inheritance. It's, I know it's a minority position, but I'm quite convinced. Why? Well, because it correlates to essentially the only part of Python where you really have to use inheritance, because the way the except clauses work totally relies on inheritance. You can't do it otherwise. So if you do have to use inheritance, you can't adopt the normal principle, prefer composition over inheritance, then the multiple inheritance may come in handy. Specifically, suppose there's a kind of type error that is, for example, any kind of standard exception will do, that is very specific to your module or package. What I like to do then is define, I would normally call it my type error or something, but I don't have space on the slide, so I called it my T. I inherit from the class error I defined before, which means this is an error coming from my own package, and then from the standard exception that I actually closely resemble, in this case, a type error. This means that a client that would need at this point to catch all type errors and doesn't care where they're coming from exactly, can catch type error. That will work. Multiple inheritance and except clauses work just fine. And a different client which wants to catch all exceptions typical only of your module can do that just as easily too, so you get the best of both worlds. And this concludes the first half, the tactical part of, okay, this is how you handle exceptions in Python. Now we move to the much more interesting part, and not all that different between versions 2 and 3, which are error handling strategies. So I was responsible many, many years ago for introducing this terminology to acronyms to define the two big classes, big categories of error handling strategies. LBYL, EAFP. You can spell it out, look before you leap, versus it's easier to ask forgiveness than permission. But if you're discussing this a lot, the phrases are a bit long, you want to use the acronyms. Why was that important, and possibly still is? Because people who come from many other languages have become, where exceptions are really a big problem to have, strive, go overboard to avoid any exception by using LBYL strategies. The LBYL means first, check all the preconditions are met. If they're not, raise the exception or give some other indication of error. Only if all the preconditions are met, perform the operation expecting no exception. The easier to ask forgiveness than permission, which, by the way, is a phrase I borrowed from one of the most amazing women ever to bless computer science, Grace Murray Hopper, is simply just try performing the operation. Any prerequisite violations, Python will catch for you. The exception will raise. You may want to catch to raise something different or do cleanups or whatever. but you're done. No huge bunches of code checking prereqs. Why? Well, because LBYL has problems. First of all, it breaks one of the principles I enumerated earlier. Never check something that Python will check for you anyway. It makes no sense. LBYL duplicates work that Python performs anyway to check the preconditions. Next, and even worse, it obscures code clarity. You can have 5 or 6 lines of code which do the actual work, buried after 50 lines that just check if everything is hunky-dory. That's not the way to help readers and maintainers of your code. If you have to check a lot of preconditions, you're quite likely to forget some, in which case the exceptions you didn't expect will happen anyway. So you have to be ready to handle anyway. So why all the wasted pre-checking? One of the worst cases, things change all the time. Pantarei, things change. Suppose instead of just trying to read a file and catching the file not found error, you did, well, I'll first check if it exists, and only if it exists, we'll read it. Well, news for you. It existed when you checked, and then some other process running on your machine may have deleted it. You can't control that. It's another process outside of your control. So this is exactly the example shown in both ways. I wish we had time to go over the LBYL version and spot all the many possible problems. But essentially, I've written down to, if some file exists at the path, well, open it and return its content. Otherwise, return the default value. While the other version is the one I already showed as an example of the new exceptions, like file not found error. The second one is rock solid. If anything is a problem, it will either raise an exception. For example, suppose the first one would raise the exception too. Suppose path is a dictionary. Then you can't open it as a file. That's an exception, but according to the function specs, that exception needs to be raised, and so it does. So once having been converted to the Grace Murray Hopper School of Programming, easier to ask forgiveness and permission, how to do it right, narrow down as much as possible the area in which you're guarding against exception. That's absolutely crucial. The first version is a very natural way of doing things. So the try-call specifications are try-calling a method called attr on the object called obj with arguments saying, okay, star A, star K. If that attribute is not present, then return a default value instead. And so a very natural way of doing it is just do the getAttr. If that's an attribute error, then return the default, otherwise go on with the call. What's the problem here? Well, this catches not only an attribute error raised by the getAttr you can see on screen, that is, there is no attribute or method attr in obj, but if there's a bug in that method which causes a completely unrelated attribute error, this also returns a default instead of propagating the attribute error as it should. So this is the second version is EAFP done right. In the try, only do the getAttr and use a little local variable to get the result of the method as the method. It's also more readable, that's a side benefit. Catch the attribute error to return the default only for the try clause, and this is a good example of using the else clause to be very explicit about what is not guarded by this try statement, except clauses. So this is a trivial example because I needed to fit it on a single slide, but it applies to more complicated cases even more so. Don't guard too many operations in a try clause. In general, large programs, a program that's twice as big gives you more than twice as many heartaches as the one that's half as big. One of them is in error handling. You have to think, even in the architecture of your program, about all possible cause of errors. There could be errors in your code. Unfortunately, errors in the libraries you use. No library is 100% debugged. Those are the place for unit tests. If you do find bugs in the libraries you use, send the unit test as a patch or pull request, as they say these days, and ideally the fix too. But this is what unit tests are for. If any bug survives your unit test, then you don't have enough unit tests. Just add the unit test to your suite as soon as you notice the bug. It should be caught by your unit test. Subtler are mismatches between the prerequisites of the libraries and your understanding. These you can't really fix with unit tests. You may mock the library, but your mock will behave as you think the library should behave, not the way the library actually behaves. So that's why we have integration tests, where you're actually running your code calling the library, or if it's a framework, calling back to you. Third, and actually pretty frequent, invalid inputs to your code. This is where try except is really your friend. Not so much for errors caused by bugs or misunderstandings of how a library works. But it's when you take external input, which is outside of your control. You're never going to be able to unit test or integration test a human being that's interacting with your program. And unfortunately, as we all know, human beings are still in release 1.0 beta, and they've been for a while. And I do not expect any improvement anytime soon. So this is where you want to try except. Python will check things for you. You just don't want to crash when it does. Sometimes you'll add a few more tests for very specific stuff, very specific to your program and arrays. The same goes when I say inputs, that includes human interaction, also includes a configuration file or some environment variable, stuff that some human being directly or indirectly would have set. Inputs in this sense. Then consider, whoops, I caught a bug. Now what? Well, I can just crash and show a beautiful traceback. Well, there's one thing, the area of programming is very vast and varied, but one thing I am absolutely sure of. Any program that shows the user a traceback is broken. I don't care what. It is a broken program. Why? Because the info that the coder needs to understand and fix a problem is never the same the user needs to at least understand, ideally remedy, like make the input correct. Never show the user a traceback. It's maybe important information for you, archive it somewhere, ask the user permission to please send it to you. There's many ways to deal with it, but what you want to show to the user is an error message that's a core part of your user interface. You realize it or not, users who are just meeting an error are in an emotionally fragile state. They particularly need friendly messages, not 500 lines of Java traceback or even just 50 of Python traceback. I mean, it's a bit better, but not by much. Focus on what can they do? What should they do? Like, please enter a number above 17, or if there's a simple problem in one of their inputs, or we're very sorry, we'll be back to you as soon as possible with a fixed version, whatever. Once you've caught, diagnosed, and blah, 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 your program, if at all feasible in your architecture, restart it. You may try, oh, well, I can fix all of the ways the state had been invalidly altered and go on. Maybe you can, more likely than not, you'll miss something. Just if you can possibly restart, of course, that works better if at various periodic intervals, when you're sure things have been doing well so far, you snapshot the state of your program to files or databases or somewhere so you can restore it from there. Ideally, since your program might end up in completely unusable state, having a separate watchdog program that looks for a heartbeat or a health check or something and kills your program and restarts it as needed may be viable. But here we're getting into advanced architecture. Just simply restarting your program and exec in any Unix-like system, for example, would do it. Logging is your friend, your bestest friend ever. You may be scared of it because it's so rich and complex. That's because it's used in a huge variety of situations. It's worth your effort to understand at least that subset of logging that you will be using all the time. That's how you debug. That's how you optimize. Even if there's no bug, but things are a bit slow, how do you follow what's happening on the server? Make sure your logs are machine-parsable. You don't want to spend hours staring manually at mostly repetitive log and hoping you can spot the point where things aren't as they should be. Then design your log parsing scripts just as carefully as you design any other part of your code. Once you've done that, when in doubt, you think, should I log something here? The answer is yes. I don't need to know anything else. You think that maybe at some point that information could be useful for debugging or whatever, log it. That makes very large logs, right? Which is why first you make sure you can have the computer deal with them. Don't log just errors. I've seen people with otherwise excellent program do that. They only think, oh, wow, this is broken. I should log the state. OK, what would the state be if things weren't broken? Oh, whoops, I don't log that. Because that's logging. That's what logging.info is for. Gives you a base case comparison of how the state should be. Last but not least, far from least, avoid assert. Unless you're using some weird testing system which changes the meaning of assert and so on. Let's not get into that. It seems an attractive way to check sanity, right? For example, I have my function. Well, I'm not using type checking yet, so first thing, I said assert is instance exint. Apart from the type checking polemic, don't use assert. It's an attractive nuisance. It's there to trap you and hide bugs from you, because it will become an operation whenever you run with -o. But have you debugged your users? Have your users, you can have debugged your software. Maybe. I've heard somewhere of big program without any bug. I suspect it's a legend, but maybe it exists. But is there a user who never makes a mistake, never gives you wrong input? I very, very much doubt so. Moreover, what people assert usually checks stuff that Python is checking anyway. So it's kind of a subcase of look before you leap. Just don't do it. The only reason assert is there is while you're developing, doing sanity check, not on inputs, on internal state, and provide so-called executable docs, although I prefer doc strings and the doc test module for that. OK, so this is the non-Q&A part of the talk. I remind you of those two URLs. The first one is to get, and please wait, give me a couple hours to have lunch and then update the slides. And the second one is to get copies of the book. And please send me feedback.
So, just before lunch, we have 5 minutes for questions. If you have a question that you want to ask, come here to the mic.
Hey, so my background is with Common Lisp, and it has some similar issues. And with the loop before your leap thing, the concern would be that it invokes a lot of overhead with manipulating the stack and stuff. So
I'm sorry.
Do you want to speak to, in the look before you leap case, it can be very efficient to just check a particular simple thing as opposed to, it seems like there would be a lot of overhead to conjuring stack traces and stuff. Are those done lazily? Can you speak to the performance implications?
In terms of implementation, exception handling in Python compared to, say, a function call doesn't really add overhead to the extent that, say, it would in C++. It's the same order of magnitude. So considering that anything you're planning to check that Python will again check for you internally is going to be a function call, I do not really see any advantage there. So there's another situation which I wish. So let's say if there's a key foo in the dictionary, then I want its value. Otherwise, I want the value bar as a default. There used to be a lot of angst about, well, I can save a nanosecond by checking if key in the dict, well, as long as it's almost never there, yes. If it's there 99% of the time, then definitely not. On the other hand, why not try except a key error? The right solution is, of course, to use the get method of the dictionary, which is designed to do only one hash lookup and the check internally for you. That's why so many of my examples are get-like. That is, do this or give me this default value. It's really a good pattern or idiom, if you will, but it appears in so many different situations. Apart from those, there's really no good case for loop before you leap. Seriously.
Hi. Thank you for the talk. About the context, the dunder context object on the exception. Will it do this more than once if there's several? And is there any control flow significance, or is that output trace its only purpose?
So the exception that propagates is the one that was raised last in execution order. Its context, if any, is the exception that was being handled in the lexically closest, is that right? No, execution-wise closest except clause. There is no infinite stack of contexts. Okay. But the exception that is the context can in turn have a context.
Oh, yes, that was...
That's not forbidden, or a cause, or both. You could have a raise from something that sets the cause, that's very explicit. It might also implicitly set the context. On the other hand, I believe I should check, the except hook in the top-level interpreter only shows you one. So you need a custom except hook if you are in the habit of nesting except, try except forever.
Oh, thank you.
Hi, I have a question about whether checking first or be sorry. So I have seen a lot of checking first when people want to provide a really good error messaging. So you check for things, and the message that you can tell the user is very specific, while if you let Python just check in array and throw everything if it's not found or something, the error can be less specific, and it's harder to add that on the static handling. So I was wishing to know how you deal with that, how you add proper messaging.
How to deal with what? I'm sorry, I just
that, yeah,
can't-
in
don't
this
understand.
comparison of either check first on B or be sorry and do things later, I have seen that kind of approach when people
I'm
want
not
to do.
sure I understand what you're asking about, but in general, the only reason to check is that if you didn't check, Python before repeating the check would do some immutable, some irretrievable mutation of state. And there is essentially no cases in most sane systems. One might be, you know, you want to write 2 gigabyte to disk, you might want to first check that the disk has the space. That's because nobody's going to check until the disk is full, and then you've only written a part. If writing a part of the data is worse than writing nothing, that might be a case. You are going to be in trouble anyway, because other processes could be writing at the same time, so it only ameliorates if you're already short of disk space. If you're running short of the space regularly, my recommendation would be to buy bigger disks, but you could check and resize the disk dynamically. If you're running, at least if you're running on Google Cloud Platform, you can resize the disk while your program is running. Resize a virtual disk under you. Depends on the operating system. If you're running Windows, that doesn't work. But with most Linux version, it can react to a disk increasing dynamically.
Okay, thank you very much, Alex. And we can continue the talk at the question session in the hallway. Thank you.